thank you, Alexi, for the awesome introduction. Thank all y'all. This is a ridiculously large coming out. I didn't think anyone would be that interested, but clearly I was wrong about that. And thank you, Dave, a lot for organizing, and of course, Nitro for hosting the space. So, for anyone who's played around with text and NLP, you know that it's a really messy affair because you have to teach a computer about the irregularities of the human language. You have to, and lots of ambiguities, and you have to teach it a sort of like hierarchical and sort of sparse nature of English grammar and vocabulary. But at Stitch Fix, when a client says that she's in her 3rd trimester, we know that she's pregnant. And when she says that she used to wear scrubs, we know that she's in medicine. And when she says that she's taking a trip, we know that she wants a fix for vacation clothing. And so this is sort of the power and the promise of word vectors, is being able to remove a lot of these ambiguities and make all of these different concepts a little bit more similar. So before I start, I want to talk a little bit about myself. I'm Chris Moody. That's my Twitter handle. What was the hashtag that we were using for this? SF Machine Learning, is that what it is? All right. So please feel free to use that. I was Caltech physics. I went to PhD. I did a PhD in astrostats and supercomputing at UC Santa Cruz, so not too far away. I'm a scikit-learn contributor. I wrote the latest version of TSNE, which is a dimensionality reduction technique, and it makes really pretty like visualizations for high-dimensional data, which is sort of like this top right diagram over here. And now I'm at data labs at Stitch Fix. And so this is an awesome job because Stitch Fix tremendously values high risk, high reward research and high risk, high reward work. And that means that I get to play around with lots of different stuff like Gaussian processes, tensor decompositions. I'm a contributor to the Chainer deep learning framework as well. But anyway, Stitch Fix is a really, really awesome place to work. And if you guys think so too, certainly be happy to chat about that afterwards. Cool. All right. Say what? OK. So you guys can't just hear me on my voice? OK. All right, great. So I'll talk into this then. Cool. So today I want to talk a lot about a few things. One, I want to explain WeirdoBEC. And I'll try to go through a little bit quickly because I feel like a lot of folks already know a lot about that. I want to talk a little about LDA, which is a similar text algorithm. And then at the end, I want to save a little bit of room for some series experiments that I made over Christmas that I've been calling lda2vec that tries to mix and hybridize a lot of the ideas that are inside of WeirdoBEC and LDA into a single algorithm. And I don't think we'll have time for this, but it's a bunch of fun stuff out there. If you see this presentation online later on, you can look at it. But there's all kinds of really cool applications for WeirdoBEC on graphs, not at all having to do with text, for recommendations. So if you use Spotify, the Discover Weekly that comes in every week, it gives you this recommendation for a new playlist. That runs on WeirdoBEC, right? But it doesn't actually use text at all, which is really interesting. But anyway, lots of cool stuff, but lots of good nuggets to go read about later on. All right. Before I start, I really want to give credit to all of these folks. Tomas Mikolov, David Bly, who invented WeirdoBEC and who discovered LDA, or wrote LDA, I should say, respectively. And then Chris Olah is a Peter Thiel fellow. He has this really awesome blog with these really, really cool visualizations of neural networks, of word representations, how LSTMs work. Really goes nuts. Radim Rahurek wrote the Python Gensim package, which is a really nice way to get into WeirdoBEC in Python. Omer Levy and Yoav Goldberg are academics, and they connected this great big body of work with WeirdoBEC back to sort of more traditional NLP statistics like PMI. We'll talk a little bit about later on. Richard Socher is the CEO of MetaMind, and he has this awesome NLP Stanford class. Xin Rong and Tim Hopper both give these really lucid explanations of how LDA works and the sort of like the technical details, the mathematical derivation of the gradient behind WeirdoBEC. Really awesome stuff. All these things are links if you do find the talk online. OK, so this example, right? King minus man plus woman equals queen. And this is what made WeirdoBEC famous. And this sort of blew open certainly my brain when I first read it, because a computer can actually do this, right? So a computer takes the word king, subtracts the word man, adds the word woman, and when it evaluates what that answer should be, it gets queen now. So you start to think that maybe the computer actually understands what these words mean. Maybe it can actually solve these analogies cleanly, right? Like it understands that the biggest difference between king and queen is the same as the difference between man and woman, namely the gender. So that's really, really remarkable because we didn't have some table that was like, oh, king, that's man, or that's like a male, and queen, that's female, and like women, that's female. We didn't have a list of attributes. We just learned this from a bunch of raw text, right? And I think that sort of simplicity gives this algorithm a lot of leverage and a lot of power. Great, and a few other things. People like to say that this is like a shallow algorithm. It's not deep learning. Okay, fine. But it's not a super big difference. It's just sort of semantics. And also, a really nice thing is that it comes pre-trained. You can actually download the word vectors. You can use them on your own corpora. You can calculate differences between those words yourself, which is a really nice thing to do. OK, so I'm going to talk a little bit about how the WeirdoBEC algorithm actually works. So like a lot of machine learning algorithms, you're going to set up some objective function. You're going to randomly initialize all of the parameters. And then you're going to do gradient descent, trying to minimize your objective or maximize your objective in some way. OK, so the challenge here is that I'm going to actually try and not ever mention neural networks once throughout this entire talk, right? Too late. Well, after that. And so what we're going to try to do is learn this one word vector from its surrounding context. And if you're thinking about NLP, maybe you're thinking about n-grams and you're thinking about transitions between n-grams, or maybe you've played around with TF-IDF and you've built a matrix of terms and then what terms are in what documents, and you've tried to factorize that matrix and now it's LSI. Okay, this really isn't that, right? This is really, we're going to try to learn the embedded representation directly with no intermediates, and we're going to try to update it with every single example. So let's say that we give it the sentence, the fox jumped over the lazy dog. What we're going to try to do is maximize the likelihood of those words given the word over. So we're going to try to maximize the likelihood of the given over, and fox given over, and maximize the likelihood of jumped given over, and so on and so forth. And so this is very much a bag of words model. There's no state that's going on from word to word to word. That's remembering where I am in the sentence, that remembering that, oh, I just had a noun, maybe I'm expecting a verb to come up next. So those things are more like Markov models or CRFs or like LSTMs. It's not like that at all. All of these words could have been jumbled up inside of that window, and it's not going to pay attention to that order at all. Still, it's a pretty simple assumption, because all you're doing is trying to predict one of those words given one of the other words. And aside from that, there's no other really big parameters that go into this. All right, so what should that kernel be? What should fox given over be? So first of all, you're Tomas Mikolov, and you're trying to write WeirdoBEC, so it's going to have to depend on word vectors in some way. And so you're going to say, OK, fox given over is going to be the same thing as the vector for fox given the vector for the word over. And we're going to randomly initialize them. We're going to have a small twist. We're going to have two vectors for every word, and it should depend on whether it's in the input context or in the output context. I'll explain what that means in just a second. So in this case, the input, the context vector, is going to be the word over. And our output word is going to be the word the. And we're going to try to maximize seeing that pair of words. And we're going to try to maximize the probability of fox given over and jumped given over and the given over and lazy and dog. And so this is the innermost for loop inside of WeirdoBEC, all right? We're going to have this central pivot word, and then we're going to go back a few words, and we're going to forward a few words. And within that window, we're going to take all of these pairs, and we're going to try and maximize the likelihood of those pairs. OK. Now, there's one for loop just outside of that, and we're going to switch from the word over. We're going to now start training on the word the. And we're going to say maximize the likelihood of the given the, and fox given the, and jumped given the, and over given the, and lazy given the, and dog given the. So this is now the double for loop right inside of WeirdoBEC, right? So I start with one pivot. I have some window around it. I look at everything in that window, and then I move the window over one. OK, so that's kind of it. So this kernel is kind of important, but that's why I think it's so weird and a kind of a disservice whenever we start talking about this big, giant neural network that doesn't, I said it twice now, sorry. And I think it's actually a little bit simpler to understand it. It's just sort of like a double for loop, and it's maximizing these two little things. OK, all right. So what should this kernel actually be? What should v out given v in be? So now we've defined this sort of high-level update path. Now we just need to talk about this little kernel inside of it. And it's going to boil down to what's the difference between v in and v out. We want to make them as similar as possible whenever they show up a lot together, and we want to make them really dissimilar if v in and v out really never co-occur. So in this case, we're going to use the inner product, the cosine similarity, if it's normalized. It's not too big of a difference. But you could have imagined other things. You could have said, hey, maybe I want to minimize the Euclidean distance, or if I'm getting really fancy, maybe I want to minimize the Mahalanobis distance, or other things. But in this case, we're going to use the inner product. So to remind you, the dot product has these sorts of properties. When the vectors are really, really similar, in this case, they're kind of pointing in the same direction, they have kind of the same magnitude, they're going to be around 1, at least if it's normalized. And so that means things like Canada and snow, which are maybe related words, they're going to have an inner product that's kind of like 1. On the other hand, like if you have words like Canada and desert, maybe the inner product's going to be kind of like 0 because those things aren't that similar. In this case, the vectors are going to be slightly orthogonal. And if they're like actively dissimilar, like very negative in the same dimension, then you're going to have an inner product that's closer to -1. And so that means that the dot product is always bounded from -1 to 1, at least when they're normalized. But we'd like to measure a probability in some way, right? Like this, I can't have negative probabilities, but I have some sort of measure of similarity. So how do I get from similarity to a probability? And that's where the softmax comes in. And the softmax function is very critical to lots of other like machine learning algorithms, and so I want to dive in a little bit into it. So the softmax is really, really, really similar to a logistic function. You might have heard of a logistic function before, and that maps you from a scalar to a binary outcome that says, given some score, how do I map this to a true false? Softmax, on the other hand, is given some score, how do I map that to a categorical outcome, to one of n outcomes? And what are my n outcomes in this case? The n possible words I could have chosen. So given this input word, what are all of my other possible choices? Everything in my vocabulary, and I'm going to score each one of them by the inner product of those two things. And so softmax is, so that vector inner product is giving us similarity, and that softmax is mapping from similarity to probability. Okay, so here's the actual form of the equation. This is just proportional to, this is the top part of the equation. And so it's just going to exponentiate the inner product of those two things. And so that inner product was going from -1 to 1. And so now that exponential is bounded to just positive numbers. OK, whatever. But now I'm going to normalize by all of the other possible things it could have been. So now on the top-hand side, I have the two word vectors I saw. And then on the bottom side, I see all of the other possible choices it could have been. And so this has two effects. One is that top side, is the numerator, is trying to push those two word vectors closer together. It's going to push those two word vectors that I just saw, try to push them a little bit closer, try to make them almost the same, right? So try to push those word vectors to be aligned. On the other hand, I really want you to push all of the other word vectors that I didn't see farther away. And so that's what this softmax function is doing. And so that's going to be the probability of v out given v in. And so this is the kernel inside of WeirdoBEC. And every time I have that double for loop, every time I have a pair of words, I'm going to try and measure this thing and try to measure this probability. And so what I'm going to do after I measure that probability, I'm going to do gradient descent on that particular probability. And I'm going to say try to maximize that probability, move the vectors in a direction that will make my probability a little bit higher. And so I'm not going to go through the derivation of that gradient. It's kind of lengthy and kind of boring. But like, that's generally the idea. And what's really cool is that this is actually relatively simple, right? I have a double for loop, and I'm optimizing one thing between two words. And it's relatively simple. And what's amazing is it's really fast. And fast enough that you're reading billions and billions and billions of words in every day. And so that's actually one of the most powerful parts of WeirdoBEC, is the fact that you can cover so much data that you start to learn all of these. You have lots and lots of observations for every word vector. OK, so I did lie a little bit. There are actually 3 different algorithms inside of WeirdoBEC. And I'm going to talk about just 2 of them. And this is the second of those. And this is the Skipgram negative sampling algorithm. And in this case, before we were doing a softmax decision. We were saying map this score or whatever to one of n different words. In this case, we're going to want to make a binary, a logistic choice. And the question that we're asking of our data now is, did this come from our data set? Did this pair of words, this context and this other word combination, did that come from our data set? Or did we completely pull that out of thin air? And so what's really interesting is that this thing is actually like trivially solved by just having the context vector equal to the word vector. So that means that if I only give you examples from the data set, then this algorithm will tell you, yep, all of those things are from that data set. And you'll be like, OK, well, you were never wrong. And you perfectly optimized that loss function. So what you need to do is give it some negative samples. Give me some samples that didn't appear in that data set. And so that's when we add another term to this equation. And we're going to say, OK, I'm going to still use the same context word. I'm still going to use that central pivot word. But I'm going to now randomly draw a bunch of other word vectors from anywhere in my vocabulary. They didn't appear in that window. And I'm going to say, make sure that you can discriminate between my fake samples over here and the real ones that came from the data set. So this is slightly different than the question we had before. Before we were like, OK, given my word vector, pick out of like the 10,000, 100,000 other word vectors, make sure that like I pick that one. What's the probability of that? In this case, I'm asking a slightly different question. In this case, I'm saying, given those two words that were in that were observed, make sure I can discriminate them from my random sort of adversarially drawn negative samples. And so one twist that happens in real life is that you actually have multiple negative samples and just one positive sample. Okay. And this is sort of a parameter you get to pick in the WeirdoBEC model. Now, what's really awesome, and what Omer Levy and Yoav Goldberg showed, and this is what I think made them really famous and sort of blew open a lot of like NIPS work, is that this Skipgram negative sampling model is completely equivalent to matrix factorization. That means that like if you've done PCA before, if you've done SVD before, if you played around with matrix recommendation algorithms before, you've probably done some amount of matrix factorization. What's really cool is that algorithm we just finished talking about that was trying to discriminate things that were from my data set from things that were definitely not from my data set is equivalent to this, right? And so that's really exciting because that equation just comes from sort of more traditional NLP. This connects WeirdoBEC. This makes it feel like it's not completely out of the blue. This connects it right back to a lot of like traditional academic work. Okay, so PMI is this point-wise mutual information. It's fancy, but the actual equation is actually super simple. And it's just an information theoretic a measure of association, like how associated are C and W in this case. So let's look at this for a bit. So it's PMI of a matrix, and your matrix is a co-occurrence counts. So in this case, how many times did the word dog show up in the same context as the word fox? You're going to write, OK, I went through all of my Wikipedia corpus or whatever corpus and said, oh, 8 times they were in the same window. And then, I guess in Wikipedia probably more than 8, but like, just for illustrations, how many times did dog and Siberia show up in the same context? Oh, once. Maybe dogs are really rare in Siberia, and maybe those two words are really like unlikely to show up in the same context. Foxes, on the other hand, they're running around Siberia everywhere, and so like you put in a 4. And so you think that those things are really similar. And so this is what we're doing with the PMI. We're just going to take this matrix and we're going to say, all right, take the number of times fox and Siberia showed up in the same context, and so that's that top. The number of times fox and Siberia were in the same, and then normalize by the number of times I've seen fox everywhere, and the number of times I've seen Siberia everywhere. And so that numerator, or that denominator, is really just controlling for the popularity of the word fox and controlling for the popularity of the word Siberia. And that's really important thing to do because words follow this power law distribution. Like the word the and the word and, that's like every other word, right? So you need to control for the popularity. Just because the word the shows up there doesn't mean it's really related to the word fox just because they co-occur frequently. You need to control for the fact that those words are very popular. And so this is really just getting right back into how much are those things, like once you remove popularity, how much are they really related to each other? And so that's what this measure is, right? And it's actually relatively simple. And so it's really, it's beautiful to me that like the algorithm that we wrote before that performs so magically well can actually be simplified into just these kinds of co-occurrences and connected to this great big body of work in NLP. Now what WeirdoBEC only does is it actually adds this little term hanging off to the right-hand side, and it's a minus log k. It's really just a bias. It's a constant. It's really kind of unexciting. And it's kind of remarkable that like you shift all of this thing over, and then that's WeirdoBEC. And so what this is effectively doing is it's down-weighting really rare terms, and it's making more frequent words so that they're more weighted. And again, that makes a lot of sense because words follow this power law distribution. Don't necessarily spend so much time, so much like computational effort, so much algorithmic effort trying to model like the really rare words. You really want to get the words that you see all the time correct. And so that's what this is saying, downweight the things. And it's this weighting that fundamentally makes WeirdoBEC different from all of the other algorithms that come before it. OK, well, this is sort of a mess of a slide, but it's really pretty that you can actually show this proof in just a few lines. And I won't do it here, but you guys can look it up later if you're super curious. All right, so qualitatively, how well does WeirdoBEC actually work? Let's look at what are the words that are really similar to Redmond. And WeirdoBEC is in the bottom row, and the Redmond is that first or second column. In previous models, they were like, oh, Conyers and Lubbock and Keene, those are all the words that are similar to Redmond. It's like, those things, at least to my eye, those things don't have anything to do with Redmond. But if you go down to WeirdoBEC, oh, it's other Redmonds, Redmond, Washington, okay, fine, other spellings of Redmond, but Microsoft also shows up there, and that makes sense because Microsoft is actually located in Redmond. All right, well, what are the words that are similar to ninjutsu? You get ninja, you get martial arts, you get sort of, okay, that's great. Those are obviously like very, very, very similar sounding words. Okay, fine, but maybe you don't really believe qualitatively the results. Like, let's start looking at the quantitative results. And the way you do this, you start by testing analogies. You ask questions like, king is to man as queen is to what? And the answer is woman. And then in that case, it would be a semantic analogy. And so that's the third column from the right. But you also have syntactic tests, in which case you're asking questions like, walk is to walking as run is to what? And the answer is running. In this case, you're testing, like, did you learn the gerund form of these words? And so it's a little bit more grammar, and you're not asking things like gender anymore. Cool, all right. Anyway, it does remarkably well. It certainly beats the pants off of everything else before it. And there's like things that like have come and improved on WeirdoBEC, but like this is sort of like an impressive benchmark for a very first thing. So what's actually happening when you add king and man and woman together? So I kind of want to try to drive some intuition about what word vectors are and how they mean and how they sort of interact with each other. So let's load up all of our word vectors. In this case, I'm just showing just 4 of the words, but we have 100,000 words. And I'm showing just 2 of the dimensions, and there's 500 dimensions. So it's kind of like as if we'd effectively PCA'd it. And we're going to take the difference between man and woman. So remember that we're taking king plus man minus woman. So we're going to take that difference. And we get this vector. We're going to load up the word king, and then we're going to take that delta and add it head to tail, right? Kind of just like how we did in kindergarten, or maybe not kindergarten, but. And we're going to have some resulting vector. In this case, it's going to be 0.3 and 0.9. Lives somewhere in that space, just a set of numbers. We're going to have our other 100,000 word vectors that live out there, and we're going to try and find the closest word vector to that one. And of course, voila, we're going to find that the closest word just happens to be the word queen, right? And so this is how we're solving king minus man plus woman equals queen. And so queen just ends up being the resulting vector. Now, what's really, really, really interesting is that this red direction always encodes gender, right? So the difference between man and woman looks exactly like the difference between king and queen. And that means it's always feminine. And it's not just for those 4 words. Like, you can go out and out and out and find it for other words, right? So the difference between aunt and uncle is exactly that vector too. The difference between daughter and son is that vector too. And so that means that, like, after a while, you start to see, look, this pattern is like, okay, whatever. That direction must always mean that we're going to move in the more feminine direction. Cool. So we have hundreds and hundreds and hundreds of different directions, right? We have a 500-dimensional space. That means at least another direction might be higher status, right? That was the difference between man and king, for example, or the difference between woman and queen. But we have another 498 dimensions, so what do they encode? Let's start looking at some examples, right? So, we live in this vector space where operations like addition and subtraction aren't just sort of like mathematical concepts, they're like meaningful in a lot of different ways. So check this out, right? Like, Czech plus currency, you get koruna, you get Czech crown. That's perfect, right? That is definitely the Czech currency. Vietnam and capital, you get Hanoi, right? German and airlines, you get Lufthansa. How awesome is that, right? Like, so Lufthansa, like, you start to really feel is like a perfect mixture of just German and airlines. It's really cool to think of these vectors as just being additions of other ideas and of just vectors and ideas being sort of interchangeable. And that in fact, that you can add and subtract these ideas to create other concepts. Cool, so yeah. I'm not sure I could hear you. Oh yeah, so the question was, why do you have multiple words? And so it goes back to how have you pre-processed your document. In this case, they've applied a preprocessor that takes lots of commonly co-occurring words and then transforms them into one token. Like, you can kind of think of it as just like taking those words and then like adding underscores in them. Saying that, yeah, that like Ho Chi Minh City is secretly like one word, right? Which in and of itself is its own algorithm and an interesting thing. How do you actually go from 4 words to 1 token? But we'll talk about that. Yes? you're going to have to say that again.
So if you combine, say, I don't know, Czech and Vietnam,
Yeah.
Or just words that we don't expect. Okay. If you just combine words at random,
yeah, so you'll.
Is the nearest neighbor larger than the pairs like these?
Oh yeah, absolutely, because there might not be a word that lives at that point in space. So the question was, if you take, Vietnam and add a completely, like, ridiculous word to it, like Vietnam and, I don't know, Scala, right? You're like, I don't know what the combination of Vietnam and Scala is. And certainly you'll calculate a resulting vector for that. And then you'll try to figure out what the closest word vector is to that point. And you might not find anything. Or, I mean, you'll eventually find something. You'll eventually go far out enough that you'll find something. But it might not be that similar. It might not be that close. Yeah.
What if you have a word that has multiple meanings? The meaning vector might be pointing out as my opposite.
Yeah, that's a really good point. The question here is like of like polysemy. Like how do you, what happens when one word has the same morphological form, but has different semantic meanings? For example, you could imagine that like the noun form of this is very different than the verb form, or maybe that it just has multiple meanings. Part of that is answered that like you live in this very high dimensional space, so you can actually point in lots of different directions at the same time. That takes care of some of it. But another really interesting thing is that you can actually go through and pre-process this and change every instance of one token with like, oh, I recognize that it's actually in the noun form, and I'm just going to say currency just in the noun form, and then just literally add like underscore noun to it, and then learn a new WeirdoBEC learning on that, which is actually a blog post that came out by I forget his name now, but the Spacey.io folks who actually talked about sense2vec like last week or 2 weeks ago. It was really hot on like Hacker News. But if you're interested in that, I would definitely look up sense2vec. They try to take care of exactly that kind of problem, but otherwise it's not explicitly handled. Okay, so I'm going to keep moving on. Definitely like running a little bit slower than I wanted to, but definitely save your questions for the end from now on. Sorry. Okay, so what I really want to do is now I've learned these word vectors. Let's start adding them together with stuff that I have at Stitch Fix, right? So in this case, I want to take item 3469. Which I don't expect you guys to know. It looks kind of like this. And I want to try to add the word pregnant to it, right? And so people write back, they get particular items, particular pieces of clothing, particular pieces of fashion, and they write back their reactions to them. And in this case, they might say, I really love the stripes in this, and the cut around my neckline was amazing. But someone else might write something about it being gray and black. Maybe they like that, maybe they didn't. But either way, WeirdoBEC is going to start picking up on that subtlety and that nuance in the language, and it's going to start associating that with the token for this item. And so you have lots of this sort of interaction of order a Wikipedia amount, and far too much to actually sort of manually annotate, but this is perfect for like a WeirdoBEC algorithm that's going to just run over all of this text. Okay, so fine. So we add these two word vectors, and the result is we get these other word vectors are really similar. Okay, but when you look at what items those represent, you get this, and I was sort of amazed, right? Like this actually worked really, really well. I found other items that were black and white and gray and stripes. But like you can see, like the model is wearing a maternity bump, right? So these are explicitly made for our maternity line, and they're safe for expecting mothers. And you can see even the item on the far right, you're going to have sort of similar tones and similar colors, but this time it's flowy, and it's great for expecting mothers. Okay, so there's a bunch of stuff I didn't really mention. I'm going to skip this slide, but it's a lot about how to actually do this stuff at home. There's a lot of problems with dealing NLP. It's still really messy. You got to clean it up. Databases kind of suck at like looking at like word vectors and calculating differences and doing linear algebra on a database. It's kind of terrible. And you can do it, but it's not fun. And like any machine learning algorithm, you're going to have false positives. So now I want to talk a little bit about LDA. And so this is LDA run on our data set, right? So we have lots and lots and lots of written about every single item. And so some of our items, we have more words than the collected works of Shakespeare, right? And so we just know the crap out of all of those attributes, right? And so that means that, and so if we take that space and we project it down to a two-dimensional space, so this is a T-SNE dimensionality reduction diagram, you start to get clusters in it. And so this is one of them, right? So this is the sort of the clunky jewelry cluster. And somewhere else, you'll see a dangling, delicate jewelry cluster. And so we aren't looking at the images at all here, right? Like, or rather, the algorithm didn't look at the images at all. These are things that clients describe like in the same sort of like most cohesive fashion. Like it's like sort of contrasty, big, clunky jewelry. Another cluster over here is going to have topics on patterns, on styles. So this cluster is going to be tops that are all similarly described as being sort of high contrasty and with colors that sort of pop. It's really cool that we can see this space, right? No longer are these things like completely disparate like items. They actually live really close to each other. Maybe like you want some bright dresses for like a warm summer night. And when I was writing this, we had just launched our maternity line, so this is why I'm talking about it so much. But this is a maternity cluster, right? And so you can see that people who are maternity talk about it in a very specific way because, when you have a baby, your clothing needs to change very, very, very quickly. What's really neat is that it's not just visual topics, not things that are really readily apparent, like zippers or like colors or different kinds of fabric. You also get lots of topics about fit. Right? So, and that's very, 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 very important, right? Like how someone describes how their neckline, how it fits on their arm, how it hugs their midsection, or maybe it flows out really wide, is really important. And it's very much catered to every single person's body. It's going to be completely different. Capturing those topics is extremely important to us and is how we try to deliver personalized service. Okay. So I love both WeirdoBEC and LDA, but I really want to talk about how actually they're really kind of similar. But they come from completely different communities, right? So when you look at the WeirdoBEC paper, you get this sort of like big, giant neural network diagram. It's got like a bajillion different parameters going on and lots of different, you look at this, you're like, man, that's why it's so awesome. It's got so much crap going on. And then like the LDA, like graphical model over here is the complete opposite. And the Bayesians love to do the complete opposite. It's like, look, this is the simplest, most elegant model I could have possibly written. And, it's got a whole 5 letters in the whole thing, right? In both cases, you have no idea what's going on. But I think it's kind of neat to, they're actually more similar than they are separate or different. Cool. So I want to talk about how WeirdoBEC is actually a local algorithm. And it treats the whole world like it's one very, very long text string, no end of documents, no end of sentences, and it's just this window sliding across words, right? So I have one word predicting another word. But your text probably looks a lot like mine. It's actually organized in some way. I have some client comments column, and I probably have it indexed by something. And in fact, what LDA is going to do is it's actually going to take advantage of that index to try to predict all of the other words inside of it. So in LDA, you have documents that are globally predicting words inside of that document. Or sorry, you have document vectors that are trying to predict all the words inside of it. And so this makes a really big deal when you get to things like, less so like client comments like this, but much more so like when you get to legal documents or medical documents, which are tens of thousands of words. And then the difference between WeirdoBEC and LDA is huge. Another big difference is how you actually represent the vector. WeirdoBEC is going to be all real values. You're going to have numbers like minus 0.75 and plus 2.2. The LDA vector, on the other hand, is all going to sum to 100%. And one of those values is going to be 78%, maybe another 11% here, a 0%, and 9%. To visualize that, WeirdoBEC sort of looks like this, right? It's like a bar chart. It's got some things going up, some things going down. But the LDA vector is a lot simpler to visualize because it's got very, very few components. The way to think about this is the WeirdoBEC vector is more like an address. It's kind of like 200 Main Street. 200 Main Street is not twice that of 100 Main Street, right? But you can figure out a lot about 200 Main Street by looking at the neighborhood around it. Something similar is true of WeirdoBEC. Right? You can figure out words that are similar to that. Hold on, I'm running over time. I'll get your questions at the end, sorry. So it's much easier to say to another human being that this topic vector is 78% of something. But it's really hard to say that in a WeirdoBEC vector that it's, this word vector isn't plus 2.2 of anything. And it isn't minus 1.25 of anything else. But the LDA vector is 78% of something, and it's a lot easier to interpret that. And this starts to get a really big deal when you go to high dimensions, right? And WeirdoBEC is going to be very high dimensional. And LDA is going to be just as high dimensional, but it's going to be sparse. And that means that like if you can kind of barely see it, it actually has like some mass at 9%, some mass at 78%, some at 11%. And the rest of those other components, all 97 other components, are going to be 0 or really close to 0. WeirdoBEC, on the other hand, is going to say, oh, it's a little bit of this, a little bit of this, a little bit of this, and another 100 like little bits of this, right? So it's really hard for a human to sort of interpret what all of those numbers actually mean. On the other hand, it makes it extremely flexible, right? you can be similar to another word vector, at least for a 100-dimensional one, in 100 other ways. On the other hand, the LDA document vectors have fewer ways they can be similar or separate, but they can be far more interpretable. And I'm going to argue that that's because of two big critical properties of algorithms. One is that it's a mixture, and two, that it's sparse. Sparse means that it had most of those elements being 0, mixture meaning that you can decompose it as a sum of other things. Okay, so the question is, can we actually do both? Can we try to combine the best ideas in lda2vec, or the best ideas of WeirdoBEC and LDA in lda2vec? So this is a bunch of experiments I ran over Christmas, and it was super, super promising, and it's been really fun to talk about them since, but definitely take them with a grain of salt, just experiments. So this is our typical table at Stitch Fix. We have WeirdoBEC. It's trying to learn some word from some other word nearby. LDA, on the other hand, is trying to use that document vector to predict all of the words inside of it. But you get these really, really awesome topics out of it, right? So if she says, I love finding new designer brands for jeans, you know that that document is 80% in the high fashion topic. And if some other one says, I love the color, the pattern, and the flowiness, you know that that document is 60% in the style topic. That's really, really awesome, because then I can go back to my CEO and say, oh, look, the number of people talking about high fashion has been changing a lot over the last few months, and we really should order some more high fashion clothes or something like that, right? This is the kind of impact, right? This is how you can sort of steer a ship and steer a business, by having interpretable machine learning models. Something that is a lot harder to do with WeirdoBEC. Not impossible, but hard. And this is especially important for things like fashion, because trends and styles are rapidly changing. It's a really fun problem to try to stay ahead of them. All right, so again, WeirdoBEC is predicting locally. In this case, the word awesome is trying to predict the word top. LDA has some document vector trying to predict that one word, this top. So the question is, how do we actually combine this, right? Can we actually try to have predictions features coming from the document vector and from another local word vector? And I think the answer is yes, and we're going to do this by just saying okay, predict the output word given the input word plus some sort of document vector. Right? So we're going to combine that input pivot word with some document vector. And that's going to be nice, because that document vector is going to capture these sort of long distance dependencies, and that word vector is going to capture very much the short distance dependencies. This is actually a really, really similar idea to paragraph vectors in doc2vec, and that actually means that they actually know it works. And unfortunately, though, that document vector is extremely uninterpretable. It kind of looks like this. And it's about as interpretable as a hash, right? It's kind of just a bunch of numbers. It's kind of an address, but it's hard to tell. On the other hand, what I really want is an LDA vector that looks like this. Most of its math is in 2 or 3 components. The other 90-some components are 0. And now I can actually come back and say to my CEO, look, this document is this percentage in this topic, and 30% in this topic, and 70% in that topic. And I can start to analyze that. I can start to do all kinds of BI on it. Great. And so what we're actually missing are things like mixtures and sparsity. And we're going to do this by taking this document vector, and we're going to try to make it into a mixture. And it's actually pretty simple to make it into a mixture. You say, hey, that document vector, it's actually going to be decomposed into a bunch of other word vectors. And so the intuition here is that earlier we saw that Hanoi is Vietnam plus capital, right? So we know that we can tear apart Hanoi and tear it apart into at least two other word vectors, Vietnam and capital. And we know that Lufthansa can fall apart into Germany and airlines. So what I'm really hoping here is that V topic 1 will be my Vietnam, and that V topic 2 will be my capital, and that if this document is about Hanoi, I can decompose it as those two kinds of things. So we know that document vectors can be additions of word vectors. When I did this, you can start to look back and say, okay, well, fine, I figured out what that topic vector was. What's it really similar to? And you can start calculating that. Oh, it's similar to Trinitarian, Baptismal, Pentecostals, Bede, which turns out to be a monk, Schismatics, excommunication. Oh, this must be the religion topic. And I ran this on the 20 newsgroups data set, which is sort of a canonical NLP data set that comes in lots of packages. Okay, let's look at what the other topic vector is similar to. It's Milosevic, absentee, Indonesia, Lebanese, Israelis. Oh, this must be the sort of a politics or maybe international politics topic. And what you get at the end of the day is that those individual topic vectors look basically like word vectors. And then those purple coefficients, the A and the B there, are going to tell me how much of that document is going to be in the religion topic and how much of that document is going to be in the politics document. And once you interpret what those topic vectors are, you can start to figure out what almost all of your document's vectors are. And so that's why mixture models are so powerful for interpretability. So to be clear, each one of those documents is always going to have the same sort of topic vectors, the same components fixed. But the weights for each one of those documents is going to change. So everything's going to have a little bit of like religion in it, and everything's going to have at least a little bit of politics in it. But if it doesn't actually have that much politics, it's going to be pushed down to like 0% or like to 1% or something. Now, the first time I did this, I failed to make those coefficients sparse. And so I was getting things like, oh, it's plus 0.75 in the religion direction and minus 1.25 in the politics direction. I was like, what the hell does it mean to be minus 1.25 in the politics direction? The math works out, right? Like I can add and subtract word vectors, but I can't, intuitively, it's really hard for me to figure out what's the negative of politics, right? What's the negative of Canada? What's like the negative of like what other random word, right? And so when you start to look at this, and if you have 100 other topics, those individual coefficients start to look kind of like this. You kind of just have this big mess of numbers, and it's really hard to figure out what's actually going on. It's hard to figure out what's happening when you have more than just a few coefficients. So this is a trick that we can steal from the Bayesians. We can say, hey, look, I want these coefficients. I want to place a prior on them. I want to regularize them in some way. I want to say, hey, look, these coefficients should be drawn from a Dirichlet distribution. I'll explain the details in just a second. But basically what this is going to do is it's going to make everything sum to 100%. So right now these numbers are like minus 1.25 plus whatever. And they should all be percentages, so they're between 0 and 1. And it's actually going to do another nice thing for me. It's going to penalize lots of non-zeros here. So instead of having this distribution of coefficients looking like this, which is trying to say plus 0.75 in religion, minus 1.25 in politics, and then there's 98 other topics, it's actually going to say something like this, right? So now I have tons and tons of zeros, and now I can go back to my CEO and say, hey, look, this document could have been in 100 different topics. Instead, it's in these 4 or 5 topics, and nicely enough, these 4 or 5 topics add up to 100%, right? So that means that I can say, yep, it's 20% in religion, 40% in politics, and 8% cars or something like that, right? And so this is what it means to me anyway, for it to be interpretable. This is a lot easier to figure out what it means. This is a lot easier to do analytics on. It's a lot easier to share this. It's easier to put this in a database. All these nice things. Okay, so now I'm going to go and dive into the technical details. So we're going to start off with the Skipgram model. So remember way back when we were saying, hey, this pair of word and context, did it come from a real data set, or did you pull it from a randomly sampled random word? And what we're going to say is we're going to start to decompose that context vector. That's the C there. And so that's the pivot word, and we're going to say it's the addition of that pivot word, that's that first W, plus the sum of all these components and the projection onto those components. So the context is the green thing. The bases are the purple vectors. The weights on those bases are the black coefficients here. And all these things are going to live on the simplex. They're all going to add up to 100%. And so this is actually going to look kind of a little bit different than Gaussian. So if you guys are actually familiar with a lot of neural network models, this is actually really, really similar to an attention model. Attention model that's a little bit more explicitly Dirichlet and sparse. And so the idea here is that that V0 is going to be religion or politics or something. And then those A's are going to be Dirichlet distributed. And so this is actually a ridiculously simple loss function, right? This loss function, basically when you add it, makes your stuff look a lot more like it's going to add onto a simplex. It's going to make it a lot sparser. And it's so simple that I really think we should be doing this more often in deep learning, right? Because it yields highly interpretable results. And it basically transforms my nasty sort of high dimensional vector that has mass all over the place to this thing that's very sparse, has a little bit of mass in a few spots, and in those spots I can interpret those spots and tell you what it is. Great, so did we actually accomplish the objective that we wanted to? So in this case we have back to this database table, and I have all this really interesting information, right? I have all these words, they're sort of grouped up by document. WeirdoBEC is only going inside of that one field. LDA is reading it using the fact that these things are grouped by document. And lda2vec is going to give me pretty awesome results here, right? Like it's also going to tell me that like, oh, this document is high fashion. It's going to tell me just like LDA that this document is 60% in the style direction. But what's really interesting is that we can start to add more and more and more features just by adding terms to our context vector. So in this case, I might have a zip code like feature, right? So that makes a lot of sense, right? Like this client is maybe in Texas, maybe they're like in Vermont, but if they're in Texas, they're like I should be able to predict the next word coming up. It's probably going to have something to do with hot climates. If they're in Vermont, there's probably going to have to do something with outerwear. If they're in San Francisco, maybe I'm going to start talking about hoodies all the time, right? So I want topics over all of these different zip codes, and it's as simple as just adding another component to like the context, or what I'm calling context, right? So in WeirdoBEC, context was just one word, but in lda2vec, I can take that one word and add a document vector, and I can add a zip code vector to it, and then I can decompose those vectors to give me topics over all of zip codes, and I can decompose that client vector that document vector to give me topics over different documents. And so we can keep going and going and going on, and like maybe the next column in my database is client ID, right? And so here's a question that every business wants to answer: What are the different kinds of clients that I have, right? I would love to know that client ID 5977 is like sporty. I would love to know that someone else is always really interested in casual wear, and this is where if someone says that if she's in her third trimester, we can identify a future mother, right? And if she says that she's in scrubs, we can identify that she's in medicine. And so this is as simple as just adding another feature to our context vector. What's really neat, and something I don't have a ton of time to talk about, is that you can also make sure that these topics are supervised. So they predict some sort of other outcome. Normally we're just trying to predict the next word in the sequence, but we can also try and make it predict like some outcome, like whether that item was sold or not. Or maybe revenue went up last month, and I would like to know, what these topics, how they correlate with revenue, and how much they. And so that helps us align topics with our expectations, right? I would love to be able to come back to my CEO and say, hey, look, last month, like revenue went up or went down, maybe because FedEx screwed up all of their packages. If I don't have any FedEx data inside of my database, how am I going to learn that? I'm not. But you know what? All of our clients are writing back, and they're telling us systematically things, like they're telling us like what went wrong and what went right. All we have to do is listen in a quantitative way, right? So we can do that now, right? We can now start to understand that data. We can start to understand, oh, there were a bunch of package issues in January. Maybe that's like what caused revenue to go up or revenue to go down. And that's what it means to have really interpretable machine learning algorithms. We can action off of them easily. Okay. So lda2vec is developed out in the open. You can go to lda2vec.com. This is some documentation. It's showing that it's like out there and alive. It's not great documentation. It has a lot of like reference and sort of API references. There's some examples up there, but it's not totally. All right, so I don't actually have this on my screen, so it's gonna be a little bit difficult to actually look at. But one of the things that I think really holds back NLP in general is the inability to visualize it. It's really, really easy. We have 1,000 different ways to visualize numerical data, but with text, it's really, really hard to show different visualizations for it. And I think this gets us a little bit closer. So this is like one of the products that you get out of lda2vec, and it's actually this wonderful package called lda2viz, and it's also an R called lda2viz. And so let's look at some of these topics, and we're gonna definitely push my ability to read at a distance. All right, so okay, here we go. So here's topic 28, right? And ahead of time, I've picked that there should be 50 topics, and oh, I forgot to actually mention that this is actually run over the Hacker News client comment corpus, right? And so let's look at like what the most popular words in topic 28. It's like, oh, it's declarative programming, procedural programming, type classes, type classing, OO languages, FP language, pass. Okay, this must be like a programming topic of some sort. Like you can imagine like new articles like about Scala or about like Julia or pick your favorite language. They might be classified into this topic, right? So like let's pick another topic. Let's go. Okay, here we go. Topic number 9. Good recruiter, equity, more equity, option pool, total comp, current salary, exploding offer. Oh, okay, all right. Well, that's definitely about like, you know, late stage interviewing and you've gotten some sort of offer and like there's lots of people in Hacker News that are like, you know, worried about that. What's really neat is this tool lets you actually slide between like extremely like rare words that show up a lot in that topic and balance that out with like extremely common words that are also show up in that topic. And so you'll actually switch between, this is really important for things like medicine, where you have extremely rare words all the damn time, like some random medicine that you've never heard of. And if you change this lever, it'll make a little less sense with Hacker News, but like if you change this lever for medicine, you'll go between these like very, very esoteric medical words that only show up in that topic. And you'll change it more to like symptoms and conditions and things that like you and I can actually talk about. So it's a really useful lever to switch between rare, but extremely in that topic, and like more common, but a little less concentrated in that topic. So what's neat is that you'll get a diagram like this over every single component, right? So you'll get this over all your zip codes, over all of your client IDs, over all of your documents, right? You get one of these diagrams for each one. And so that lets you understand the rest of the features in your data set. All right, let me try to get back. Cool, all right, so that's all out in the open. It's on GitHub. There's some examples, there's API docs. It runs on the GPU. It's, up until yesterday, all the unit tests were passing. So have that as you will. But I think here's the big takeaway, right? So if you want really human interpretable document topics, use LDA. It's a great model. It's virtually written in every single language. There's lots of like scalable algorithms for it. If you want machine usable, word level, token level features, use WeirdoBEC. And if you've exhausted both of those things, I would use lda2vec, right? I would definitely use LDA and WeirdoBEC long before lda2vec. But if you really, really, really want topics over users, over documents, over regions, and you want to sort of like supervise those features, and you have a GPU and you want to wait for a few days, then I would use lda2vec. A quick example here is you can actually do this very, very quickly. It's like only 4 or 5 lines of code. I realize y'all probably can't actually read that, but it's instantiating the model, and then it's declaring the fact that like you're going to have a bunch of these extra categorical features. You're going to have features, in this case, this is the Hacker News model, that you're going to have features over different stories. You're going to have features over different author IDs, so on and so forth. Okay, so this isn't where this story stops either. I think you can actually do this for LDA to LSTM. So in this case, everything we were talking about today was a big bag of words model, but it'd be awesome if I could just say, give me a sentence that's 10% about religion and 80% about politics, right? And then just the LSTM just goes forth and spits that out. If you guys have seen like LSTMs and deep learning neural networks type stuff, they're really impressive, really cool, and they can spit out really cool sentences. Another thing is that we're working on our team at Data Labs at Stitch Fix is TJ Torres, who's a good friend of mine. He does a lot of deep learning on images, right? And so fundamentally, the only thing that we really did in lda2vec was compress a vector into a particular set of like very sparse states. You can do the same thing over images, and wouldn't it be really cool if we could say this image is like 10% stripes and like 5% this, and then like another 25% like zippers or something. Although maybe that's a bad example. But like it'd be really neat, and he can actually generate these images, right, from a particular vector. So it'd be really cool to just generate new images with slightly different characteristics. And I think that moves us into the domain of generative fashion, right? We can start generating new clothes. We can start saying, oh, I want something that's kind of like this, maybe the same colors, maybe the same fabric, maybe the same patterns, but I want it to actually have more stripes than the last thing, or fewer stripes, or not stripes at all. And so I think it'd be really cool to do interpretable models within like this deep learning, like variational autoencoder images framework. Cool, all right, you guys have been an awesome audience. I apologize for keeping you guys so late, and I can try to answer some questions of it all. Thanks. Let's start on the right, I guess.
For your TC and LDA algorithm, how do you determine the number of topics?
Yeah, determining number of topics is always hard. It's never it's basically the same game as you have in LDA. You know, maybe you do some elbow plots. Maybe you measure like perplexities. Perplexities are like how you. Sorry, the question was how do you measure the right K, the right number of clusters, the right number of like components in LDA. The problem with like things like perplexity measurements is that they don't actually correlate with how humans perceive the different topics and labels. So there's a really awesome paper of where people look at the LDA scores that come out. And you can say, oh, this model with more components fits better, but different humans will disagree with that notion, despite the fact that the score is getting better. So there's definitely something to be said there about the actual LDA score is not working that well, which is the usual proxy for determining what K should be. Yeah.
What's your approach to inference, and are you able to handle a lot of vocabulary words in your LDA model?
I mean, you handle out of vocabulary words the same way as you do in WeirdoBEC, which is not really. You know, like you can continue, you can basically try to restart the algorithm and add and inject some new tokens and then try to train them.
Vocabulary from your LDA model and your word vector
I mean, they're trained jointly. So like the word vector in LDA component is the same as the WeirdoBEC component.
and inference?
Yeah.
No, what's your method for inference?
I'm not sure.
Are you trying to use MCMC, gives?
Oh, no. So in this case, you're going to just use gradient descent the entire time. So it's neither. Yeah, this is at all, like not at all like a, yeah, I get, so LDA is usually solved like through EM approaches or like variational inference approaches. This is not that at all. Like this is setting up an objective function and then minimizing it. Yeah.
As you add more factors, you have inclined to use it. So you could just train use it by itself with factors. You can also use inclined by itself. You can also train jointly. Do you find that the meanings or the constituent parts change as you add more factors?
That's a good question. The question was like, as you add more and more context vectors, do you find that the word vectors change in some way? It's a good question. I imagine they do.
There's probably a diminishing returns.
Oh yeah, I would, maybe. I don't know actually. I haven't actually looked. Adam.
Have you thought about using this with deep walk and doing something similar with like community detection?
That would be cool. So Adam's question is, should we, WeirdoBEC's been applied to like these graph algorithms. So you can do this thing where you usually have a window sliding across a sentence and you say, predict this word given the next word. But deep walk, as Adam's talking about, is more about like, let's make a sentence out of individual users who are connected in, say, like a Facebook graph, right? So I might be friends with Adam, and then Adam might be friends with Dave, and Dave with Alexi. And so now my sentence is Chris, Adam, Dave, Alexi. And as I go across it, I'm moving that window, and I'm trying to make those word vectors for Adam and Chris and Dave all be really similar to each other. Anyway, it's a really, really cool algorithm. But the question is that like you could probably add context in some way to those things and try to figure out different communities. And it would be really cool because the communities you would find would be sparse and they might be Dirichlet distributed. And that might lead to like sort of interpretable communities. So maybe you would find, I don't know, like the young people community in Facebook and like the old people, or like maybe you, if you ran it on just mine, like you would find my high school friends and my college friends. But I don't know, it'd be neat to go do that. It's a good idea. Oh, Jesus, all right. Okay, I'll jump to this side of the room. Yeah. Hey.
In some of your previous examples, we were labeling topics with words from our corpus.
Yeah.
One detail that I didn't quite get is, are we constraining the topic vectors to be linear combinations of word vectors from the corpus, or are we just picking a nearest neighbor as a label for
Yeah, so there's two questions there. One is, are we constraining the topic vectors to be a word vector?
or linear combination?
Or a linear combination. So no, the topic vectors live in the same space as the word vectors, and they are essentially other words in my vocabulary. And then my document vectors are going to be linear combinations of those topic vectors. Is that your whole question? Yeah.
Isn't a topic vector a linear combination of words that are in the
So a document vector is a linear combination of topic vectors. A document vector is let me see, make sure I said that right. A document vector is a linear combination of topic vectors. And those topic vectors live in the same space of word vectors, but are not necessarily exactly the same as a word vector. So for example, like if I went back, right, so let's go back to this guy, right? So in this case, I'm calling it religion, but I made up that label, right? So initially, it was really just.
Where do these vectors come from, the topic vectors?
They're learned jointly with everything else. Yeah. Yeah.
Have you tried this on analogies? There's an interest in A is to B as C is to D, and you predict D based on A is to B is C.
That's an easy question. No. No, I haven't tried. I really should. I haven't really tried like a lot of quantitative analyses of this stuff, mostly because it's kind of hard. The analogies is a pretty good test, but you know, like maybe it would be as good as WeirdoBEC, or maybe slightly better, or maybe slightly worse. That's not really what I care about, though. What I care about is like having multiple contexts and like learning about those contexts, like learning what the zip code should be. Is it like in the hot climate topic? Is it, or learning about this client? Is she sporty? Is she client? And so you can run LDA over those individual individual columns, but in this case, you're learning them all jointly, and you can add all kinds of extra things like supervised stuff. So the analogies is good for WeirdoBEC, and it's totally amazing, but it's less useful for me trying to inform people in a business.
So that's an example of a logical relation.
Yes, that's right. Yeah, no, you're totally right. Like it'd be a good thing to check and see if like the WeirdoBEC things still pop out. Yeah.
So slide maybe 4 or 5 back, we get the 2 bar charts, the 2 group bar charts, and you showed like how like you have like a very messy mass of topics and how it distills into a couple of really salient topics.
Yep.
Could you go over that once more? I'm not sure if I totally follow.
Sure. So let's pretend like we never placed that Dirichlet prior on this equation, right? So now we're just at this. And this is really, really similar to paragraph vectors, to doc2vec, to document vectors. And so what happens here is that those coefficients, the A0s and the A1s, J's, is that they're constrained to live anywhere in the real space. So they can be negative, they can be plus 93.5, they can be minus 17. And what happens is that when you let the model fit something like that, it has a lot of freedom, right? And it finds that the really good model fits are like a combination of lots of different components, of a little bit of this and a lot of that one, a little bit of this one, a lot of that one. And it doesn't try to concentrate the components in just a few pieces. Now what happens when you say, okay, I want to take those A's and I want to regularize them in some way. And I'm going to do this with this fancy Dirichlet likelihood, right? And when that happens, you're going to instantly penalize most of these things. You're going to say, look, like if you are anything but 0, my loss function is going to be huge. And so that means that like when you get the results at the end of the day, you get something that looks like on the right-hand side. Now that does mean that you've added things to your loss function, and that might make it a lot harder to fit the model. But when you do finally fit it, it's going to be a lot more interpretable because it's only in a few bits and pieces. Does that make sense? Yeah.
I'm curious about just getting an intuition for WeirdoBEC.
Mm-hmm.
And so in terms of the gradient descent approach, the way that it sort of tries to push words that occur together to be similar vectors, intuitively that would indicate to me that you would group words that co-occur together in the same space, space.
That's right.
Why I'm missing the power of being able to do analogies. Like I don't like I get what the algorithm's doing, but I'm missing why it's as it is.
That's a really good question. The question is, great, we saw this whole algorithm, we saw how it works. Where in that did we start solving analogies? Is that roughly right? So what's interesting is that because you have these, let me skip back to this, is that somehow, because of the loss function that we set up, we managed to have these linguistic regularities. So something about that softmax, something about decomposing our co-occurrence matrix, something about saying these two things are similar in some way, helps us get to these kinds of regularities. And once we have these kinds of regularities, we can solve analogies. But the link between softmax or Skipgram negative sampling and these kinds of like linear regularities isn't totally clear to me. Isn't totally clear to me. Like, I don't see why this thing completely falls out of the loss function that we set up. Yeah, some of it still does feel like magic, yeah.
And the second question I had was, does WeirdoBEC have to be a neural network model, or could it also be blended?
So I don't think it had to be. The question is, does WeirdoBEC have to be a neural network model? I mean, like, the way I tried to explain it was it's really not like a neural network model at all. But, you know, I think like you can recast lots of different things. I bet you could recast LDA as a neural network model. You can think of LDA as optimizing a document vector and word vectors too, right? You can certainly think about it like that if you want. It's not usually how people use the language, but you can. Okay, so I know I'm way over time, so I'm actually going to stop it here. And then we can actually have questions sort of like after.
We have to do the strata winning question.
The strata winning question. Oh, okay. Oh, that's right.
It randomly chose Twitter. How big does the corpus need to be for lda2vec to work well?
That's a good question. So I've actually gotten pretty reasonable results on small data sets, like the 20 news groups data set. I haven't tried things smaller than that, but that data set's like 2 or 3 megabytes of text, I think, maybe, right around that. And it's worked reasonably well, right? So like basically, well, reasonably well is like there are 20 news groups in that data set, and you know they exist there. If you don't tell the algorithm about it, does it recover those topics, and does it recover those usenets groups? And the answer is like, yeah, pretty much. You know, you get some religion topics, you get some politics topics. So it's worked out reasonably well there. And then I've tried to scale all the way up to like the Hacker News corpus, which is like several gigabytes. And it seems to work well there. Okay, all right, now it's last question, right?
Aaron Hardin, find me.
Okay, awesome. Thanks, guys.